All right. Let's go to that last example. We said gold melting was physical, dissolving up sugar in water was physical, sour in milk was chemical, burning gasoline chemical, and then condensation of steam is physical. All right, let's go to the next question. It says a 2-liter volume of hydrogen combined with a 1 liter of oxygen gas to produce 2 liters of water vapor. Does oxygen undergo a physical or chemical change? Let's think about that. You have hydrogen, oxygen gas going to, we need to balance that too. We'll talk about balancing later. Going to water. Is that chemical or physical? The question is oxygen the same as it was here on the other side of the arrow?
Would it be chemical?
It's a chemical change. It's still oxygen, but it's not the same. Over here, we talked about this last week. Oxygen is like this. Right. Then on the other side, oxygen has a different set of bonds to it and it's bonded to different atoms. So it's not the same. So that's totally different. So that is a chemical change. All right. Next question, indicate SI. So this is kind of what we were talking about on yesterday. Indicate the SI base units or derived units that are appropriate for the following measurements. And it says the length of, let me zoom in on that, the length of a marathon race, 26 miles, 385 yards. And it's asking us to indicate the SI base units. So what length, how would we measure length with SI units? The ones we talked about yesterday, those 7 fundamental measurements. Will we measure it in miles, yards, or will we measure it in what is the SI unit for length?
Is it meter?
Meters, good. And we know that 1 meter is 1.09 yards. All right. What about the mass? What's the SI unit for mass?
Isn't it kilograms?
Okay, we will measure the mass of an automobile. The SI unit is grams, but because it's a larger object, we can measure it in kilograms. That's exactly right. All right, what about the volume of a swimming pool? How we measure volume?
Length.
Say that again.
Length. By the length.
Okay, so volume is a little different. In SI, we measure volume in liters. Which is length times, it's like it's 3-dimensional, right? So it's length times width times You remember, if you recall how to measure volume is length times width times height. So volume is three-dimensional. So we can say that we would measure this in cubic meters or meters cubed, because each one of these is going to be in meters. So it's meters times meters times meters. We didn't get a chance to get to that on yesterday, but we'll talk about it. But it is you're absolutely right that the volume is actually a function of length. It's just three-dimensional. It's like a cube. And so when we measure the volume of anything in SI units, it's either going to be meters cubed or centimeters cubed. Let me put that. Uh-oh. Very good. All right. How would you measure the speed of an airplane? Right. Speed is going to be one of those derived units. Okay. So when you're measuring speed, you're measuring distance and time. It's a function of both distance and time. So it's going to be a derived unit. So what's our unit for distance? Or length? It's meters, yes?
Is it
Yeah.
meters per second?
And then for time, the SI unit is seconds. So it's meters per second. Right? You'll see this written as M over S. It's a derived unit, just like density is a derived unit. So for E, it says the density of gold. And density is a derivation. It's the mass. It's also derived. It's mass over volume. So we measure density. What's our unit for mass?
Grams.
Grams, good. And our unit for volume is, in this particular case, when we do density, instead of liters, or I'm sorry, meters cubed, we use cubic centimeters, because density is measuring a smaller sample size, right? So it's grams per cubic centimeter. That is the measure for density. And then 1 cubic centimeter is the same as, when we talk about volume, it's the same as a milliliter. So we also see density represented as grams per milliliter. All right, let's look at the next one. It says the area of a football field. What do you think?
Would it be yards?
But it's in SI though.
SI.
It'd be meter squared.
Good. Meter squared, because area is it's two dimensions, length and width, right? So this would be meters squared. Very good. Excellent. Any questions about that? All right, let's go to number 4. Number 4 asks to give the name of the prefix. So you always want to ask what it's asking for. So the name of the prefix and the quantity indicated by the prefix. All right. So we didn't get to this yesterday, but there's a table. Let me show you. I'll pull it up. And this is also in the book, by the way. And these are some of the smaller units, prefixes, but let me get to, I want this one right here. right? So when you look at those prefixes, right? You can see here the prefix for milli, which is a lowercase m, this is the quantity 10 to, so it's 1,000th of something, right? 10 to the minus 3. And then centi is 100th of something, 1 over 100, so it's 10 to the minus 2. That's a lowercase c. Deci is 1/10 of something, and that's a lowercase d. Kilo is 1,000, not thousandth, right? So that's a lowercase k. And then mega, giga, and tera, this is a million, a billion, and a trillion. And it's uppercase M, uppercase G, uppercase T. These you just have to commit to memory. There's no magic way to remember these. You just have to commit them to memory. And that's why the table is here. You can go over it, look at it, and commit these to memory. So let me see if I can copy this and paste it in our other document. Let's try it. Paste button. I guess I cannot paste it. All right, let's just we'll flip back if we need it. What is the lowercase c again?
Centi.
Centi. And what's the numerical value for that? 10 to the what?
-2.
Minus 2. It's 1/100th. And then this one is what? Deci, which is what?
10 to the minus 1.
Yeah, 1/10. Good. What about uppercase G? What about that one?
Giga.
Yeah, it's actually pronounced giga, but I'll take it. You're
I'm
right.
sorry.
That's okay. You're in the ballpark. And that is 10 to the what? 9th. That's a billion. So a gigawatt. How many of y'all seen Back to the Future? Anybody? Probably not. That's before most of you were born. Great movie though. But one of the parts in the movie they had to power up a car that was a time machine, and they needed a gigawatt or some several thousand gigawatts of energy to power it. But they call it a gigawatt, probably because they didn't have good science consultants on the set, but that's okay. Great movie though. If you get a chance to check it out, I think it's on Netflix or Prime or one of them. All right, what about K?
Kilogram or kilometer?
Mm-hmm. So it's kilo whatever, kilogram.
Yeah, kilometer.
Yeah, exactly. And what does that represent? What numerical value? 10 to the what?
-6? Oh, 3.
Yeah, it's 10 to the third. It's kilo. Think about it. Even though it's represented by a lowercase number, a lowercase letter, and most of the others are represented by uppercase letters, a kilo is representative of 1,000. All right. What about we'll do the P and the N later. What about T?
Tetra.
It's tera. And it is a trillion. It's 10 to the 12th. So a mega, which is over, I think it's over here. We do mega. Mega is not over here. So it's mega, giga, and tera. That's a million, a billion, and a trillion. All right. Mega is M, uppercase M. Giga is uppercase G. Tera is uppercase T. All right. Let's look at what about the M? What does that represent? What prefix?
Milla.
Yeah, good. Milli. And this is 1,000th of anything. Milligram, millimeter, milliliter, doesn't matter. It's 1,000th of a milli of whatever that quantity is. N, which we didn't see, it's on a different chart, but N is nano. Everybody has heard this term. This is the opposite of giga, right? Giga is a billion, nano is 1 billionth. So this is 10 to the minus 9. So if you wanted to commit them to memory that way, where you memorize the exponent when with, you know, the different values, you could do that, because nano and giga are the opposite. Milli is the opposite of kilo, because it's 10 to the minus 3. Kilo is 10 to the third. There's no, well, yeah, there's an equivalent for tera. It's actually right here. P, lowercase p, is for pico. And this is 10 to the minus 12. So picogram, picometer, picoliter, that's 10 to the minus 12. So that's 1 billionth with a TH on the end of something. All right. So these again, these are ones you'll have to just continue to get reps with and see and keep looking at them and keep going over them and commit them to memory. Uh-oh, wasn't trying to do that. I screwed that up. Nah, the whole thing is in columns. Shucks. Okay, let's go to number 6. Oh, well, that's number 5. I really screwed that up and I was not trying to do that. Let me just undo. I think that got it. There we go. All right. I ain't worry about that. Let's do number 5. Number 5 is a different type of question. Number 5 is asking about to calculate density based on volume displacement. So this is what we call a volume displacement problem. I actually had a really cool example to use in class the other day, but the tech went on the fritz, so it wasn't really much I could do about that. So this is what we call a volume displacement problem. So let's read it. It says a large piece of jewelry has a mass of 132.6 grams. And it says a graduated cylinder initially contained 48.6 milliliters of water. When the jewelry is submerged, this is the key right here, that is submerged in the graduated cylinder, the total volume increases to 61.2. So the volume goes from 48.6 milliliters to 61.2 milliliters. And the mass of the jewelry is 132.6. All right. So what we have mass, we have two numbers for volume that we can derive the volume of displacement. And then we know the formula for density, right? Is that right? So we know the density is mass over volume. So let's put that in. D equals mass over volume. And in a displacement problem, you calculate the volume based on the difference in the two volumes given, right? So what is the volume in this case? It's going to be 61.2 milliliters minus what? 48.6
48.6.
milliliters. That's going to give me the volume of that piece of jewelry based on how much liquid was displaced when I put it into the container. All right. Actually, I'm gonna show you that. I can show you that little animation now, but we'll do it after this. All right. So what's that? 5.6. Is that right? Or 15.6?
12.6.
12.6. Sorry. All right. So let's put that in. So the volume is 12.6 milliliters, and we know the mass is 132.6 grams. So the density is going to be 132.6 grams divided by 12.6 milliliters. And that's a derived unit of grams per milliliters. Can somebody calculate that real quick?
It's 10.5. If I'm doing sig figs correctly.
10.5 grams per milliliter. And even with that, we can figure out what that jewelry is made of. Because if we Google, somebody can Google that. Google density equals 10.5 grams per milliliter and see what comes up. I think it's gold, but I could be wrong. Anybody got it? And let me show you this while we are, hold up. While we're here. It's a really cool little simulation. All right, so we have a, let's take gold. Let's see how much it weighs, or how much, what the mass is. Let's put it on the scale. Can y'all see that? So it's 40.53 grams. That's the mass. And then let's see what the displacement volume is. It's got to be submerged, so it's got to go to the bottom. So let's see. So obviously it's not gold, 40.53. And then the initial volume you see is 25, 25.5. That's not very forgiving. Let me refresh it. And it goes up to 27.6. So write that down, 27.6 minus 25.5. And the mass is 40.53. Can somebody calculate that? 40.53 divided by 2.1, I think. Yeah, it'd be 2.1. It's 25.5. Somebody calculate that and tell us what the density of gold is.
So you said 40.53 divided by 2.5?
2.1.
2.1.
What is it?
19.3.
19.3. So we know that the example we just did is not gold because that had a mass of, a density of 10.5. Did anybody look that up?
Oh, I got the metal to be silver.
Silver. Okay. All right. So you can see now we can use these properties to determine different things, right? We know if we know the density, then we can figure out what the metal is if it's been reported. So what's the density for gold. Anybody calculated that yet? It's 40.53 grams divided by 2.1 milliliters.
Is it 19.3?
Okay, we'll take it, 19.3. So yeah, so this little simulator is real cool, and you can switch things up. You can do wood. Wood has a mass of 1.95 grams. You know, you put it in the water, it's going to float. So in order to figure out what the displacement is, you got to submerge it. You get to drag it to here. And it's 28.5, so it's 3 milliliters. Let's see. So it goes from 25.5. When you submerge it, it goes to 28.5. So somebody calculate that. 1.95 grams divided by 3 milliliters, 3.0 milliliters. Anybody got it yet?
It's 0.65.
0.65 grams per milliliter. Is that right?
Correct.
Okay.
Yeah.
Good. So you can see that these derived units, like density, if you know the volume and the mass, you can calculate the density. If you know the density and the volume, you can calculate the mass. If you know the mass and the density, you can calculate the volume. All three of those terms can be derived from that one equation, right? So for density, if density equals mass over volume times density will be mass, and then mass over density will be volume. Those are your three derivations from that. All right. Let's go to another calculation because we can come back to number 6. We'll come back to number 6. All right. Let's look at these number 7 right quick. It says how many significant figures are contained in each of the following measurements. How do we know what a significant figure is? How do we know what's significant and what's not?
I know the rule was yeah.
It's a non-zero number. Is that right?
Mm-hmm.
And depending on if zero precedes the number or if it follows the number. That's how we know. That's the quick and dirty way to think about significant figures. So think about A. What about A? What do you think?
There's 2.
2 significant figures, right? 53. Both numbers are significant. So we have 2 sig figs here. I'll just put SF. All right. What about B?
3.
3 significant figures, right? The 2, the 0, and the 5 are significant. All right. What about letter C?
3 again.
Yeah. So you saying for C that is 3 significant figures? Why do you say that?
Wait, how is it not 5?
That
If
the
it's
zeros are sandwiched in between significant figures, so we can't drop them, right? Is that right?
You said it's 5 significant figures?
If we can't, the zeros, we can't drop them because they're sandwiched in between numbers that are significant.
Oh, okay, yeah.
You see how right here you got the 2 zeros here,
Mm-hmm.
and they're sandwiched in between significant figures, so that you have to count them. All right. What about I don't want to run out of time. What about F?
2.
Mhm. So F is 2 significant. We'll talk more about this tomorrow in class. But F is 2 significant figures. And
Does that say
then
-5 significant figures?
oh no. That sig figs it can't be a negative number of sig figs. That was a dash. My bad.
Oh, okay.
My bad. All right. Or what about the last one, Chi?
3.
So you have 8, 8, and 4. All right. And then the zeros, since that you're not able to round up or round down here, the zeros here you can drop off. All right. Let's go to, oh, come on, what did I do? I'll fix that before I post it. All right. So where did we, this was 2, I'll just rewrite it. This app is getting on my nerves. And we said 3 here. All right. Let's go to the next question. It says perform the following calculations with the correct number. Actually, we'll come back to that one. Let's go to number 9. And then I want to do some calculations, and then we'll come back to the sig fig questions. And we actually are going to just tomorrow's lecture, we'll use this handout to introduce the different topics, because we're going to talk about sig figs. We're going to talk about accuracy, precision. So we're just going to keep working through, because we're probably not going to finish this today because it's like 16 questions. But between today and tomorrow, we'll finish it. So let's look here and let's talk about a little bit about accuracy versus precision. All right, and look at what the question asks. It says, consider the results of the archery contest shown in this figure. Which archer is most precise? Does anybody have a working definition of what precision is?
It's how close together your like data points are.
Yeah, so precise measurements are very close together. All right, they have a very small amount of error between them. And so if you look at the 3 boards, which one of those has data points? We'll call the points data points, but which one of those has data points that are closest together?
Uh,
You say X. Okay, I agree with that. Oh. All right, you see how these points are, they're not very accurate though, are they? Because the goal is to hit the bullseye, right? So they're inaccurate, but they're very precise because the points are close together. Whoever this archer is, they're not very accurate, but they're very precise. Look at letter B. It says, consider the results of the archery contest. Which archer is the most accurate? The goal is to hit the bullseye. So the accepted value, that's what accuracy deals with, the accepted value. So the goal is to hit the center right here, right? And so that's when we talk about accurate, we're trying to meet a point. So we want to meet, in this case, we want to meet the bullseye because that's the accepted value. So accuracy wise, which one is the most accurate?
W.
W, right? So accuracy is the closeness to the accepted value. Precision has to do with reproducibility. How close are you? How close is each data point to the other data point, right? So the precision has to do with whether how reproducible something is. Accuracy has to do with how close it is to the accepted value, right? So here the bullseye is the accepted value. So Archer W is the most accurate. Archer X, he was able to reproduce where he hit the target, although it was not very accurate. Does that make is that making sense?
Yes.
All right, let's answer that last question. It says, who is both least accurate and least precise? We only got two archers left to look at.
Is it Y?
Why? Why is all over the place, right? It's not reproducible and it's nowhere near the bullseye, right? None of his shots are anywhere near the bullseye. With Z, you can see he got a couple of shots here. That's somewhat accurate, but very imprecise because he got shots all over the place too. But this one is the least accurate. Zoom in so I can write better. The least accurate and the least precise.
So which one was the most precise?
X. It's most precise, and then this one was most accurate. With accuracy, you're trying to you are trying to replicate an accepted value. With precision, it's more about replicating about the values being close to one another. Let's look at number 10, and this might clarify. So it says classify the following sets of measurements as accurate, precise, both, or neither. So the weight of a chocolate chip cookies, and you have 17.27, 13.06, 19.46, 16.92. What are we missing here? We don't have anything to compare it to, do we? So we don't know like what the accepted weight of a chocolate chip cookie is, right? So these numbers, we have no way of determining how accurate they are compared to what the accepted weight is. So this would be neither, right? And the numbers are not very close to one another either. So they're kind of all over the place. So we'll say that this is neither. Does that make sense? Like when we talk about accuracy, we need something to compare. We need something to compare, right? Because the accuracy is based on an accepted value. Precision is just comparing the points to themselves, right? Let's look at, what about B? B says testing the volume of a batch of 25 ml pipettes. So now we know we have a number to shoot for. It's 25 milliliters is the number that, so each pipette, we're trying to see how close it is to 25 milliliters. Let's look at the values. You have 27.02, 26.99, 26.97, and 27.01. What do you think? Are those numbers precise in that they're close to one another?
Yeah.
They are. Are they accurate?
No.
It's close to 25. It's not quite 25. So they're not like super accurate, but they're also accurate because they're close enough to that target. So we can say that this is both accurate and precise. Now, those pipettes are going to need to be calibrated because the 25 mils is, if that is your target and you're 2 milliliters off of that, you need to calibrate that, but it's still pretty accurate. Now, if it was like 30, 35, somewhere in that range, then that we can consider that inaccurate. But it's close enough to be considered accurate, and the numbers are close enough to each other to be considered precise. What about C?
It's both.
It's both accurate and precise. Very, very accurate and very precise. Determining the purity of gold. All right, we got we out of time. I want to do one more. I tell you what, just make sure on tomorrow that you bring this, have this handout with you. And instead of lecturing tomorrow, we're going to have a list of topics that we're going to cover using these questions. So we're going to talk about conversion factors, and we're going to talk about, we're going to continue with sig figs and accuracy and precision. So we'll do that on tomorrow. So you don't have to turn this in yet. You'll turn it in after class tomorrow because we should be able to finish it. Is that all right?
Yes, sir.
All right. All right. So with that being said, I'm going to stop recording, and I'll post this recording too.